Hey guys, Professor Doney back again for probably the last problem we'll do for projectile motion. Two-dimensional motion, again, where the object is launched and lands at a different place. Now we're going to switch things up, make this a little more difficult in that in this problem we're going ramp to ramp, or we're going off a ramp still at 10 meters per second at 30 degrees, which is what we did in the previous problems. However, the ramp happens to be on top of a roof. So we have a different launch and landing height. The object's going to start here, go off the ramp, go up, and it's going to fall back down below the launch height here, and it falls back an additional distance. Now, as you can see from left to right, we don't quite have the symmetry we did when we went ramp to ramp in the previous problem. So we can't just say time up equals time down without doing some little tweaking on that. So we're going to see how we solve this. The books typically will go through and solve this kind of problem with using the delta y equation that I'm writing here. And they put the delta y as a negative 20 because it lands below. But that ends up giving you a quadratic. And unless you're good with math and have dealt with the quadratic equation, solving it before, I like to avoid that just because there's a lot of places you can make math mistakes. So I'm going to go through how I do this and how we solve this problem. Now again, we're doing 10 meters per second at 30 degrees. That means our velocity in the x is still 8.6 after we do the cosine, and our velocity in the y is 5 meters per second vertically once we do the sine. So we're still going to use those numbers. Now, why would you want to put a ramp on top of the roof to begin with? Well, as we can see, if we put a line across here, having the ramp throws us up again still, allows us to go up, but allows us when we fall back down to fall back an additional distance. That's the height of the rooftop or cliff or whatever we're on top of. So that gives us some more time in the air. More time in the air translates into, like this, more time, more t gives us more distance, more delta x. It allows us to land further away than if we didn't put it up there. So just in case you're into this stuff, that's what that does, but you probably figured that out. So we're going to go through, we still treat this in the up direction as a throw-up problem, and if we do the solution we did before, we're going to do v equals vo plus gt. We come out to be, our time is going to be pretty much half a second again, and we did that in the previous video, so check out how we came up with that. And then we also found out that y up through using the v squared equation, we came out to be about 1.2 meters. So this is identical to the problem previously we did on the video. There's our 1.2 meters here, and our time up is going to be that time there. So I'm not going to go through those solutions again just for the sake of time. Now for the time down, what we want to do is treat it as a drop problem. What do I mean by a drop problem? It's a free fall problem. It's going to fall from rest. And if we allow the object to get up here to its peak, the final velocity goes to 0, and then on the back half, our initial velocity now is 0 because it's now starting to fall, so it falls from 0 velocity in the y direction. So our initial velocity in the y is 0 at the peak. That's why it comes to a stop, and then it starts coming back down. So we're going to do a drop problem. I like to use this equation for drop problems. We'll call positive down because everything is going down. It's a half gt squared. We know the distance is going to fall. It's going to fall back 1.2 meters plus the additional 20. So that's 21.2 meters. It's from rest, so it's 0 plus half. 9.8, gravity is positive, and t squared. And here we find the time is going to be 21.2 divided by 4.9. Take the square root of that. That's for a little over 2 seconds, 2+ seconds. And since we're running out of time, I take that value, and to find out how far away it lands, I just go back to my x equation. That'll be the 8.6 times the 2+ seconds. That gets us in the 17, 18-ish meters away. Okay, I'll put approximate in there. We can check the exact numbers. But why didn't it give us a whole lot more distance? Well, it wasn't a very high building, and we're not going that fast horizontally. So it just added a little bit to our distance to it. But still works out. Hope that helped out. We'll see you in the next video.